Good evening to everyone. My name is Dr. C. Vasanthi, Assistant Professor, Department of Mathematics from CPA College, Real Analysis. Today we discuss about the topic real analysis. First we have to see the metric space introduction, definitions, and then next we have to see the last one is the examples. So definitions of the metric space is let f from R to R be a function defined by f of x equal to norm of x equal to x if x greater than 0 and then minus x if less than 0. If f of x equal to 0, then if x equal to 0. The first property is absolute value functions. Norm of a equal to 0 or norm of 0 equal to 0. The second one is norm of a greater than 0 if a not equal to 0. Norm of a equal to minus norm of a. The fourth one is the norm of a plus b equal less than or equal to norm of a plus norm of b. Now for x and y are real numbers, the geometrical interpretation of norm of x, y is the distance from x to y. If we define the distance function rho by rho of x comma y equal to norm of x minus y, then the properties 1 to 4, the following consequence for any points x, y is that our real numbers. Therefore, rho of x comma y x equal to norm of x minus x equal to 0. This is the distance from the point itself a point. So it's converted into 0. The next one, the second one is the rho of x comma y greater than 0, x not equal to y. The distance between two distinct points is strictly positive, and the rho of x comma y equal to rho of yx. The distance from x to y is equal to the distance between the y to x. So the last condition is the triangle inequality. Therefore, distance satisfies all the properties. So distance function is usually called a metric space. So next we have to see the definitions of the metric space. Let M be any set. A metric of or M is a function rho with the domain M cross N and range is connected in 0, infinity. 0 is the closed interval and infinity is the open interval, such that for any elements x, y, z of a set M, therefore rho of x, x equal to 0, rho of x, y equal to 0, that implies x not equal to y. The third condition is rho of x, y equal to rho of yx. Then the last condition is rho of x, y less than or equal to rho of x, z plus rho of z, y. It is called a triangular inequality. If rho is metric for M, then the order for M, rho is called a metric space. So the metric does all the properties of the distance function norm of x, y for R for the real numbers. For examples, let f from R squared to R be a function defined by f of x, y equal to norm of x minus y. So the f is metric for R. The metric is known as absolute value for M. And next we have to see the distinct metric is defined by the formula d of x, y equal to 1 if x not equal to y, if 0 if x equal to y. By definition of d of x, x equal to 0, if x not equal to y, then d of x, y equal to 1 greater than 0. Clearly d of x, y equal to d of y, x. Triangular inequality d of x, y less than or equal to d of x, z plus d of z, y. If x equal to y, then the left hand side is 0 and the inequality tends gold. Suppose if x not equal to y, then the left hand side is equal to 1. Since x not equal to y, we must have either x not equal to y or else x not equal to y. Thus we have to write answer at least 1 and the triangle inequality holds in any case. The second example is r squared with usual distance measured by the Pythagoras theorem. Therefore, the r squared is, so the points will be taken as x1, x2 and y1, y2. Therefore, the square root of x1 minus x2 whole squared plus y1 minus y2 whole squared. This is sometimes called the two metric. So therefore, it is called an D2. This is also metric space for r squared. And then z equal to x1, y1, w equal to x2, y2. We have to see the picture. The metric on the complex number C interpolated as the organ diagram. In this case, the formula for the metric is now d of z, w equal to norm of z minus w, where the norm is the formula represent the modulus of the complex number rather than the absolute value of the real numbers. So the next example of plane with the taxi cab metric d of we have to take the 2 points. Therefore, d of x1, y1, x2, y2 equal to norm of x1 minus x2 plus norm of x2, y1 minus y2. This is often is called one metric. It's called an D1. Next we have to hold the supremum point or maximum of the metric. We have to calculate the distance from the x1 comma y1 and x2 comma y2 equal to maximum of number of x1 minus x2 comma y1 minus y2. This often is called an infinite metric. To understand that, it helps to look at the unit circles in each metric, that is sets that belongs to R squared. D of a 0 comma discrete matrix is equal to 1. We get the following picture. So rho is metriconium, then 7p is also metriconium. If rho and f are metriconium, then p plus f is also metriconium. Suppose 7p is not metriconium, the second property is non-negativity, not satisfied rho. Next we have to any questions for me from metric space or group. Example 4, we have to see the next. We have to see example of not metric. Rho from R squared to R be a function defined by rho of x comma y equal to 0. Then rho is not metric since 1 not equal to 2, but rho of 1 comma 2 equal to 0 by definition of rho. Other properties are satisfied. Examples of not metric of the maximum minimum point. So the minimum of the x1 comma y1 and x2 comma y2 equal to minimum of x1 comma x2 comma norm of y1 comma y2. Then D is not metric. So we have to calculate the distance point. The minimum is become 0. So second property is not satisfied. Next, any questions? Thanks to all.